Every galaxy in the observable universe is moving away from us. The cosmos is expanding, everything racing into the void. Distance is growing, light from distant systems stretching toward red as they flee. Point a telescope anywhere, and you'll see this universal retreat. Billions of galaxies all escaping into the darkness, like embers scattered from a dying fire. This is a story meant to be heard slowly, in a calm and unhurried way. Except one. Andromeda is coming toward us. Look up on a clear night, away from city lights. Find the constellation named for the chained princess of ancient myth. There, above her outstretched arm, you'll see something most people mistake for a smudge on their vision or a thin cloud drifting past. But that faint blur isn't in your eye, and it isn't weather. It's a galaxy, an island containing more suns than you could count in 1,000 lifetimes, burning across a void so vast that the light reaching your eyes tonight left before your species learned to speak. That light has been traveling for longer than humans have existed. The photons entering your retina right now departed Andromeda when your ancestors were still apes learning to walk upright, their brains small, their hands just beginning to grasp tools. While that light crossed the emptiness between galaxies, moving through absolute darkness, where nothing exists except the occasional atom drifting alone, life on Earth transformed. Species emerged and went extinct. Continents drifted to new positions. Ice ages came and went, and still the light traveled, unchanging, moving at the fastest speed physics allows, taking so long to cross the gulf that the entire span of human civilization fits comfortably within its journey. You're not looking at Andromeda as it exists right now. You're looking at its ghost, frozen in light, an image from the deep past. Somewhere out there in the darkness, the real Andromeda exists in this present moment, but you cannot see it. That view won't reach Earth until your civilization is ancient history, until whatever lives on this planet has forgotten humans ever existed. But here's what makes Andromeda different from every other distant light in the sky. What transforms it from a beautiful abstraction into something immediate and unsettling. While you've been looking at that ancient light, while those photons have been crossing the void carrying an image from before human history began, Andromeda itself has been moving. Not away like everything else. Toward us, closer. Getting nearer with every passing moment. The movement is too slow to see. You could watch for your entire life and never detect the change. But it's real, constant, unstoppable. While you sleep and work and go about your days completely unaware, Andromeda closes the distance. Every second that passes brings it measurably nearer. Every breath you take occurs in a universe where the gap between our galaxy and Andromeda is slightly smaller than it was before. This approach violates the fundamental pattern of cosmic expansion. Everything else is fleeing. The universe itself is stretching, carrying galaxies apart, creating more space between them as time flows forward. But Andromeda and the Milky Way are falling toward each other, pulled by mutual gravity, their approach so inevitable that nothing could stop it even if we wanted to. We're watching a collision unfold in ultra-slow motion, two immense structures on trajectories that will eventually intersect. And Andromeda has done this before. It knows how to consume other galaxies. We can see the evidence scattered across space, written in light, impossible to miss once you know what you're looking for. Long streams of stars arc through the darkness surrounding Andromeda, tracing paths that don't make sense, following curves that reveal violence in the galaxy's past. These aren't natural structures. They're scars, remnants, the stretched-out corpses of galaxies that wandered too close and were torn apart. Imagine a smaller galaxy, perhaps containing billions of stars, each one a sun potentially orbited by worlds. This galaxy has existed for ages, its stars following stable orbits, its structure maintained by gravity and momentum. Then it encounters Andromeda. At first, nothing seems wrong. The galaxies are still separated by vast distances, but Andromeda's gravity is immense, and it reaches far. The smaller galaxy begins to feel the pull. The effect isn't uniform. Stars on the side facing Andromeda feel stronger pull than stars on the far side. The galaxy begins to stretch, elongating like taffy being pulled, its shape distorting as differential gravity tears at its structure. Stars that once orbited peacefully in their home galaxy are now being yanked in different directions, some pulled harder than others, the entire system straining under forces it cannot resist. And then it breaks, not with violence or explosions, but with dissolution. The galaxy doesn't crash. It comes apart, its stars pulled into long streams that wrap around Andromeda like ribbons, marking the paths where the galaxy died. The streams can remain visible for billions of years, ghostly structures tracing orbital trajectories, each stream a monument to a galaxy that no longer exists. Andromeda has consumed at least 2 galaxies this way, probably more. Each victim added to its mass, made it larger, gave it stronger gravity to capture the next prey. It has grown fat on its neighbors, a predator galaxy that feeds on anything unfortunate enough to pass within reach. And those stellar streams we can still see, those arcs of light threading through Andromeda's outer regions, those are the bones of its victims, the only evidence that entire galaxies once existed before being devoured. The scale of this cannibalism is difficult to grasp. We're not talking about stars colliding or planets being destroyed. We're talking about entire galaxies being torn apart, billions of stars scattered, structures that took ages to form dissolved in cosmic violence. And it happened slowly over millions of years, each orbit of the doomed galaxy stripping away more stars, the death occurring in glacial slow motion, but inevitable, unstoppable, brutal in its own patient way. Now Andromeda is coming for us. The Milky Way, our home galaxy containing our sun, and every star you can see with your naked eye is the next meal. We're approaching each other across the remaining void, falling together under mutual gravitational attraction, and eventually we will collide. The approach has already begun. The trajectory is set, and when the galaxies finally meet, everything will change. But to understand what that means, to comprehend what's approaching us, you need to see Andromeda not as a faint smudge, but as it truly is. Point powerful telescopes at that blur and gather light for hours through sensitive instruments, and the galaxy reveals itself. The simple smudge transforms into a vast spiral, arms winding through space, structure layered upon structure, details emerging that show Andromeda as a complex system containing multitudes. The galaxy is enormous. If you could gather all the stars in the Milky Way, every sun in our night sky, every stellar system throughout our entire galaxy, and then double that number, you'd approach what Andromeda contains. More than 1 trillion stars burn in that distant spiral, each one a nuclear furnace. Some are blue giants that blaze with fierce light and will die young in cosmic terms. Some are ancient red stars, cool embers that formed when the galaxy was young and will burn for ages yet. Some are yellow suns like ours, stable and steady, potentially orbited by worlds where life might exist. Each star could have planets, rocky worlds, gas giants, ice moons, ocean planets, desert worlds, lava worlds. The variety is beyond counting, the possibilities infinite. And among all those worlds orbiting all those suns scattered throughout a galaxy larger than our own, there might be life. Perhaps simple microbes clinging to existence in hostile environments. Perhaps complex ecosystems with forests and oceans, predators and prey. Perhaps intelligence. Perhaps civilizations looking back at us right now, seeing the Milky Way as we see them, wondering if anyone else is out there. We'll never know. The distance is too great. If beings exist on a world in Andromeda looking at Earth right now through their telescopes, they're not seeing Earth as it is today. They're seeing our planet as it was ages ago, before complex life emerged, before anything crawled onto land, perhaps before Earth was anything more than a ball of rock orbiting a young star. And if we sent them a message today, traveling at the speed of light, they would receive it in the distant future, and any reply would take just as long to return. By the time we heard back, human civilization might be extinct. Our species evolved beyond recognition or vanished entirely. Yet despite this isolation, despite the certainty that we cannot touch Andromeda or communicate with anyone who might live there, there's something profound about seeing it. That faint blur represents everything beyond our reach, all the mysteries we can observe but never solve, the limits of what's achievable. It's beautiful and terrible and completely indifferent to our existence. Humans have been seeing Andromeda for as long as humans have had eyes. Ancient peoples looked up and saw it, though they didn't know what they were seeing. To them it was just another faint patch in the night sky, perhaps a cloud or a cluster of dim stars, unremarkable among the celestial patterns they used to mark seasons and navigate. The earliest written description comes from a Persian astronomer over 1,000 years ago, noting its position and appearance but having no way to understand its true nature. For centuries it remained a curiosity, a nebula, a fuzzy object that telescopes could magnify but not explain. Some thought it might be gas and dust within our own galaxy beginning to condense into new stars. The truth was stranger. In the early 20th century, astronomers realized that Andromeda wasn't part of the Milky Way at all. It was separate, distant, an entirely independent galaxy existing far beyond our own borders. This discovery shattered the previous understanding of the cosmos. Suddenly, the universe was vastly larger than anyone had imagined. The Milky Way wasn't alone, wasn't unique, wasn't everything. There were other galaxies, countless island universes scattered through space, each containing billions or trillions of stars. And Andromeda was the first one we recognized. The closest large galaxy to our own, bright enough to see without instruments if you know where to look. It became the prototype for understanding what galaxies are and how they behave. Every subsequent discovery built on observations of Andromeda. We've studied it obsessively. Powerful telescopes have mapped its structure in exquisite detail, revealing spiral arms and dense central regions and scattered outer zones where stars are sparse. We've measured its rotation, tracked how stars orbit around the galactic center. We've photographed it in every wavelength of light, seeing not just what our eyes detect, but infrared from cool dust, ultraviolet from hot young stars, radio waves from hydrogen gas, X-rays from extreme objects. And every observation reveals more complexity. Andromeda isn't just a simple spiral frozen in space. It's dynamic, evolving, shaped by billions of years of history, bearing scars from past violence, actively creating new stars in some regions while others remain dark and quiet. It's a galaxy in its prime, neither very young nor very old, transforming gas into stars, growing and changing over timescales that dwarf human comprehension. The center holds something particularly extreme. Hidden within the dense concentration of ancient stars at the galactic core, invisible to our eyes but revealed by its gravitational effects, sits a black hole containing the mass of millions of suns compressed into a region smaller than our solar system. This monster doesn't emit light. You can only detect it through how it affects nearby stars, pulling them into orbit so tight and fast that they complete full circuits in mere years, despite being light years from the center. The black hole is relatively quiet now, not actively feeding, not blazing with the radiation of infalling matter, but it could wake. If gas clouds or disrupted stars fall within its grasp, it could become an active galactic nucleus, outshining the entire rest of the galaxy. For now it waits, a gravitational well at Andromeda's heart, anchoring the rotation of 1 trillion stars. Surrounding that central monster, stars in Andromeda's core are packed more densely than anywhere in the Milky Way. They orbit in a vast spherical swarm, their paths chaotic, creating an environment where stars pass relatively close to each other by cosmic standards. The night sky viewed from a planet in that region would be spectacular beyond description. Thousands of bright stars visible, many close enough to cast shadows, the darkness never truly complete. Beyond the central bulge, spiral arms wind through the galactic disk. These arms contain young, hot stars, blue-white giants that burn their fuel quickly and will die in supernova explosions after just millions of years. The arms also glow with new star formation, vast clouds of gas collapsing under their own gravity, igniting fusion, creating stellar nurseries where the next generation of suns is being born. But Andromeda's spiral structure is peculiar, different from textbook spirals. The arms are subtle, almost ring-like in places, broken and fragmented in others. This irregularity suggests a violent past, gravitational disturbances that disrupted the original pattern and created the complex structure we see today. Those disturbances probably came from the same source as the stellar streams, the same mergers that left those ghostly arcs of stars orbiting through Andromeda's halo. And there are companions. 2 smaller galaxies orbit Andromeda like moons around a planet, each containing billions of stars but dwarfed by the giant they circle. These satellites are doomed. Over time, Andromeda's gravity will pull them closer, stretch them out, eventually tear them completely apart and absorb their stars. This is the fate awaiting anything that orbits too close. Andromeda grows by consuming everything within reach. One of the companions is unusually dense, its stars packed into a remarkably small volume for a galaxy. This concentration suggests it was once larger before close passages to Andromeda stripped away its outer layers, leaving only the indestructible core that survives today. It's being eaten alive, slowly dissolved, its stars pulled away one by one to join the streams we can still trace orbiting through Andromeda's outer regions. The other companion is more diffuse, containing some young blue stars that are unusual for this type of galaxy. These young stars indicate recent star formation, gas somehow accumulating, despite the tidal forces trying to tear the galaxy apart. Perhaps some gas was stripped away during a past close approach, but fell back, providing fresh material for a new burst of stellar birth. Both companions will eventually vanish. Their orbits are gradually decaying, bringing them closer with each passage. Eventually, they'll be completely disrupted, their stars scattered and mixed into Andromeda's general population, their identities erased. Their galaxies dying slowly, and we're watching it happen, seeing the process unfold across cosmic time. But companions and consumed galaxies and central black holes are just details in a larger structure. Most of Andromeda, in terms of mass, is something we cannot see at all. The visible galaxy, all the stars and gas and everything that emits or absorbs light, represents only a fraction of what Andromeda actually is. The rest is completely invisible, dark matter that doesn't interact with light in any way we can detect. It's there because gravity reveals its presence, because the motion of stars and gas requires more mass than we can see to explain the observations. This dark matter exists in a halo surrounding the visible galaxy, extending far beyond the reach of the outermost stars. While Andromeda's visible disk spans perhaps 200,000 light-years, the dark matter halo extends 10 times farther, creating a vast invisible structure that contains most of Andromeda's mass. The visible galaxy is just the bright core of a much larger dark system, and that dark halo is so enormous that it's already touching the Milky Way's dark halo. The two galaxies are separated by visible matter, by the void between their stellar disks. But in terms of dark matter, they're already in contact, already influencing each other. The collision, in that sense, has already begun. Not the spectacular visible merger when stars interpenetrate and gas clouds ignite, but the slow gravitational embrace, the beginning of a process that will take billions of years to complete. Right now, at this moment, you exist within both galaxies' dark matter halos. Earth sits within the Milky Way's halo, obviously, surrounded by its invisible mass. But we're also at the very edge of Andromeda's influence. Particles from Andromeda's halo are passing through the space where you sit, invisible and undetectable except through their gravitational effects, contributing infinitesimally to the forces holding you in your chair. This is Andromeda, not just a faint smudge of light, but a vast structure, complex and dynamic, bearing scars from its violent past, surrounded by the slowly dissolving remnants of galaxies it has consumed, accompanied by satellites being gradually torn apart, all of it embedded in a halo of invisible dark matter that extends across distances incomprehensible to human intuition. And this entire system, this trillion-sun empire, this cannibal galaxy that has already devoured its neighbors, is approaching us, getting closer, falling toward the Milky Way with unstoppable momentum. The collision is guaranteed. The trajectories are set by physics laid down billions of years ago when these galaxies first formed. Nothing can alter this course. Nothing can stop what's coming. In a future so distant that the sun will have evolved beyond recognition, that Earth itself will likely be uninhabitable or destroyed, that whatever exists will be unrecognizable, Andromeda will arrive. And when it does, when the two galaxies finally meet, when they begin the slow process of merger, the sky will transform into something no human has ever witnessed. But that transformation is unimaginably distant. Right now, tonight, Andromeda is just a faint blur of light in the constellation for which it's named. It's been there for billions of years, visible to anyone who looked up, unremarkable to most, extraordinary to anyone who understands what they're seeing. That pale glow is a galaxy, a trillion suns, an entire universe of possibilities approaching us across the void. And it's coming for us. If you could somehow leave Earth, accelerate beyond the solar system's boundaries, travel beyond our sun's neighboring stars, beyond the spiral arm containing our local stellar neighborhood, beyond the Milky Way's disk entirely, and cross the void separating our galaxy from Andromeda, what would you find? What exists inside that distant spiral beyond the faint blur visible from Earth? The answer is a structure so vast and complex that seeing it from a distance reveals almost nothing about its true nature. Andromeda from Earth appears as a simple smudge. Andromeda from within would be a universe unto itself, a landscape of light and darkness, stretching across distances that make planetary systems seem microscopic. Start with the spiral arms, those great sweeping curves that wend through the galaxy's disk. From our external viewpoint, they appear elegant, almost artistic, like brush strokes of light against darkness. But those brush strokes are regions hundreds of light years across, containing billions of stars, vast clouds of gas and dust, stellar nurseries where new suns are being born from collapsing molecular clouds. Travel along one of these spiral arms and you'd encounter different environments over the course of your journey. Some regions blaze with the light of young, massive stars, blue-white giants that formed recently from compressed gas and now pour ultraviolet radiation into their surroundings. These stellar infants are violent, their radiation so intense that it ionizes nearby gas clouds, causing them to glow in spectacular nebulae visible across thousands of light years. The hot stars won't last long in cosmic terms. They burn their fuel too quickly, living fast and bright before dying in supernova explosions that will scatter their enriched material back into space. Other sections of the spiral arms are darker, filled with dust that blocks visible light, creating dark lanes threading through the brightness like veins. But these dark regions aren't empty. They're where star formation happens, where dense clouds of molecular gas collapse under their own gravity, fragmenting into clumps that will become the next generation of stars. The darkness hides birthing grounds, regions of intense activity, invisible to optical telescopes, but revealed by infrared instruments that can see through the dust. Between the bright young stars and the dark dust lanes, older suns orbit peacefully. Yellow stars like our sun, red dwarfs that will burn for trillions of years, orange giants that have exhausted their core hydrogen and begun the slow expansion toward death. These stars formed earlier in Andromeda's history, some billions of years ago, and they'll continue shining long after the hot blue giants have exploded. They're the galaxy's stable population, the long-term residents that outlast the spectacular but brief fireworks of massive star formation. Each star potentially has worlds orbiting it, rocky planets close to their suns baked by stellar radiation, gas giants farther out, massive balls of hydrogen and helium with complex weather systems and rings and moons, ice worlds in the outer reaches where sunlight is weak and temperatures drop close to absolute zero. The variety is infinite, each stellar system unique, each planet a world with its own characteristics determined by its formation history and its star's properties. Some of those worlds might harbor life, on planets orbiting stable stars at the right distance where liquid water can exist on the surface, where atmospheres can protect against radiation while allowing sunlight through. Chemistry could become biology. Simple molecules could assemble into complex structures. Metabolism could emerge. Reproduction, evolution. Over billions of years, what began as chemical reactions could become ecosystems, perhaps even intelligence. But you'll never know which worlds, if any, contain life. You'll never visit them, never see them up close, never communicate with anyone who might live there. The distances are too vast, the time required too long, the isolation too complete. You could spend your entire life traveling through Andromeda's spiral arms and explore only an infinitesimal fraction of what exists there. 1 trillion stars is not a number you can truly comprehend. It's vastly more than all the grains of sand on all Earth's beaches. Each grain a sun, potentially with worlds, potentially with life. Move inward from the spiral arms toward the galaxy's center, and the environment changes. The stellar density increases. Where the arms might have one star every few light years on average, the inner regions pack stars closer together. The night sky from a planet in these denser regions would be spectacular. Hundreds or thousands of bright stars visible, many close enough to show as tiny disks rather than points, their combined light creating perpetual twilight, even at midnight. But density brings danger. With stars packed more closely, gravitational interactions become more frequent. A passing star might disturb planetary orbits, flinging planets into different trajectories, or ejecting them entirely into interstellar space. Close encounters between stars, while still rare, happen often enough over billions of years that stellar systems in the dense regions are constantly being reorganized, planets shuffled, orbits destabilized, and radiation levels increase. More stars means more ultraviolet light, more X-rays from extreme objects, more cosmic rays accelerated by supernova explosions. Any life trying to survive in these inner regions would face constant bombardment from high-energy particles, radiation that damages DNA and disrupts delicate chemistry. Whether complex life could persist in such an environment is questionable. Perhaps only the hardiest microbes could endure, hiding in subsurface oceans or deep within planetary crusts, where rock provides shielding. At the very heart of Andromeda, within the densest concentration of ancient stars, something waits. You cannot see it directly. It emits no light, reflects nothing, appears as pure absence. But its presence is undeniable, revealed by how it affects everything nearby. Stars in the innermost region orbit at tremendous speeds, whipping around the galactic center in tight ellipses, their velocities revealing that they're trapped in the gravitational well of something containing millions of times the sun's mass. This is the central black hole, a monster lurking at the galaxy's core. It's not a stellar remnant, not the corpse of a single massive star. It's something that grew over billions of years, fed by gas and dust, and occasionally entire stars that wandered too close and were consumed. The black hole has grown fat on Andromeda's material, accumulating mass, strengthening its gravitational grip on the inner galaxy. Right now, the monster sleeps. It's not actively feeding, not blazing with radiation from infalling matter. The region around it is relatively quiet, the black hole dormant, waiting. But this quiescence could end. If something disturbed the careful balance, if gas clouds were driven toward the center by gravitational chaos, if stars collided and their debris fell inward, the black hole could wake. Matter spiraling toward it would heat to extreme temperatures, radiating intensely. potentially outshining the entire rest of the galaxy. Andromeda could become a beacon visible across the universe, blazing for a time before the fuel was exhausted and the black hole returned to sleep. Stars venturing too close to this central monster face a terrible fate. The gravitational field near a black hole isn't uniform. The side of a star facing the black hole feels stronger pull than the far side. This differential gravity, called tidal force, stretches the star, elongating it, pulling it apart if it passes close enough. The star doesn't explode. It's shredded, torn into a stream of stellar material that wraps around the black hole and begins spiraling inward. The disrupted star's material heats as it falls, compressed and accelerated by gravity, reaching temperatures where it radiates X-rays and ultraviolet light. For months or years, the dying star creates a spectacular flare, a brief bright spot at the galactic center visible across vast distances. Then the material either falls past the event horizon, lost forever, or is ejected by radiation pressure, scattered into space. The star is gone, consumed, its atoms either added to the black hole's mass or dispersed to eventually become part of new stars. This has happened many times in Andromeda's history. Stars have been sacrificed to the central black hole, their deaths creating brief flares that faded into darkness. And it will happen again. Stars orbit, and some orbits inevitably bring them too close. The black hole is patient. It can wait for its meals to arrive. Scattered throughout Andromeda, both in the spiral arms and in the spaces between, are the remnants of stars that have already died. Some exploded as supernova, massive stars that exhausted their fuel and collapsed, rebounding in detonations that briefly outshone the entire galaxy. These explosions left behind expanding shells of hot gas, supernova remnants that remain visible for thousands of years, glowing with the energy of the blast. Other stars died more quietly, exhausting their fuel and gently shedding their outer layers, while their cores collapsed into dense remnants. These dying stars created planetary nebulae, beautiful shells of gas illuminated by ultraviolet light from the hot stellar core at the center. The nebulae expand slowly, dispersing over tens of thousands of years, returning material to the interstellar medium where it can be incorporated into new generations of stars. The remnant cores themselves, what's left after the outer layers are gone, come in different varieties. Some are white dwarfs, Earth-sized objects containing roughly the sun's mass, hot but no longer generating fusion energy, slowly cooling over billions of years. Others are neutron stars, even more extreme, containing more mass than the sun compressed into a sphere just tens of kilometers across, so dense that a teaspoon of neutron star material would weigh billions of tons on Earth. And some remnants are stellar mass black holes, smaller cousins of the central monster, but still extreme by any measure. These are the corpses of the most massive stars, objects that collapsed past neutron star density and kept collapsing until nothing could stop them, creating gravitational wells so deep that not even light can escape. They lurk throughout Andromeda, invisible except when they're in binary systems with normal stars, pulling material from their companions and heating it to X-ray temperatures. Long streams of stars thread through Andromeda's outer regions, arcing across space in curves that don't match any natural structure. These are the stellar streams, the stretched-out remnants of smaller galaxies that were torn apart. Each stream marks a death, a galaxy that existed for billions of years before encountering Andromeda and being destroyed. The streams are ghostly. Individual stars within them are too faint to see from Earth without powerful instruments, but collectively they trace out coherent structures, rivers of suns following similar orbits because they once belonged to the same doomed satellite. Some streams are relatively fresh, formed recently enough that they remain tight and well-defined. Others are ancient and dispersed. Their stars spread across vast regions of sky, barely distinguishable from the general background of halo stars. By studying these streams, you could reconstruct Andromeda's violent history. This stream came from a small galaxy that approached from one direction, was torn apart over multiple orbits, and now wraps around Andromeda like a ribbon. That stream came from a different victim, perhaps larger, destroyed more recently, its stars still following closely related paths. A third stream, barely visible, represents a merger so ancient that the disrupted galaxy's stars have almost completely mixed into Andromeda's general population. Some streams contain clues about what their parent galaxies were like before destruction. The chemical composition of stream stars matches what you'd expect from small galaxies with different formation histories than Andromeda. Some streams are metal-poor, containing stars formed from relatively pristine gas with few heavy elements, suggesting they came from dwarf galaxies that formed early and experienced little star formation. Others are metal-rich, indicating more active star formation histories, possibly small spiral galaxies, with their own cycles of stellar birth and death before Andromeda consumed them. The streams also tell you something invisible. The galaxies that were destroyed didn't just contain stars. They had their own dark matter halos, invisible mass distributions surrounding the visible galaxies. When tidal forces tore apart the stellar components, they also disrupted the dark matter, creating dark matter streams threading through Andromeda's halo alongside the visible stellar streams. You can't see these dark matter streams directly, but you can infer their existence from how the visible streams behave. Two larger companions still orbit Andromeda, not yet reduced to streams, but clearly dying. The first orbits dangerously close, its path bringing it near enough to Andromeda's main body that tidal forces become significant. This doomed satellite is unusually dense for a galaxy its size, its stars packed into a remarkably compact volume. This density suggests a violent history. The satellite was probably once larger, perhaps a respectable small galaxy with its own disk and spiral structure. But repeated close passages to Andromeda have stripped away its outer regions, removing gas and dust and peripheral stars, leaving only the dense central core that survives today. With each orbit, more material is pulled away. Stars on the satellite's outer edges feel Andromeda's tidal forces most strongly, their orbits disturbed, some escaping the smaller galaxy entirely to join the streams. The satellite is slowly dissolving, losing mass with every passage, growing smaller and weaker. Eventually nothing will remain except another stream, and what is currently a distinct galaxy will become just one more ghost orbiting through Andromeda's halo. The second companion orbits farther out, maintaining safer distance where tidal forces are weaker. This has allowed it to retain more of its original structure. It's less compact than the first companion, more diffuse, appearing almost fluffy compared to the dense inner satellite. But even this distant companion shows signs of disturbance, evidence that Andromeda's influence reaches far, that nothing in orbit is truly safe. Curiously, this outer companion contains some young blue stars, Unusual for this type of galaxy, which typically holds only old, red stellar populations. These young stars indicate recent star formation, gas somehow accumulating and collapsing, despite the tidal forces trying to tear the galaxy apart. Perhaps some gas was stripped away during a past close approach, but later fell back, providing fresh material for a brief burst of stellar birth before the satellite's ultimate destruction. Both companions are temporary. Their orbits are slowly decaying, bringing them closer to Andromeda over time. Eventually, they'll be torn apart completely, their stars scattered into new streams, their identities erased. What are currently distinct galaxies with billions of years of independent history will become just more material for Andromeda's halo, indistinguishable from the other captured stars orbiting there. Dozens of smaller satellites orbit farther out, each one a dwarf galaxy containing millions of stars, each following its own path through Andromeda's gravitational domain. Some are dwarf spheroidals, faint and diffuse, barely visible even with powerful telescopes. Others are dwarf irregulars, lacking clear structure, appearing as formless patches of light. All are being slowly consumed, their orbits decaying, their outer stars being stripped away, their futures predetermined. And surrounding everything, containing most of Andromeda's mass, invisible but undeniably present, the dark matter halo extends far beyond the visible galaxy. This invisible structure is enormous, reaching out perhaps 1,000,000 light-years from the galactic center, creating a gravitational potential well that contains and shapes everything we can see. The dark matter doesn't emit light, doesn't absorb it, doesn't interact with electromagnetic radiation in any way our instruments can detect. We know it exists only through gravity. The way stars and gas move through Andromeda requires more mass than we can see, far more, and that unseen mass must be distributed in a roughly spherical halo surrounding the visible galaxy. What is this dark matter made of? We don't know. Despite decades of searching, despite increasingly sophisticated experiments, we've never directly detected a dark matter particle. We see its gravitational effects everywhere, in every galaxy we study, but its fundamental nature remains mysterious. It might be exotic particles beyond current physics, perhaps something that interacts only through gravity, and possibly other forces we haven't discovered. Or it might be something else entirely, something so different from normal matter that we're not even asking the right questions. But whatever dark matter is, it's real and it's here. And Andromeda's dark matter halo is so vast that it's already touching the Milky Way's halo. Right now, at this moment, dark matter from Andromeda passes through the space where you sit. You cannot feel it, cannot see it, cannot detect it with any sense you possess. But it's there, invisible particles moving through you, through Earth, through everything, interacting with normal matter, only through the weakest of forces. In a very real sense, the collision between Andromeda and the Milky Way has already begun. Not the spectacular visible merger when stellar disks interpenetrate and gas clouds collide, but the slow gravitational embrace of dark matter halos already in contact, already influencing each other, already beginning the process that will eventually merge both galaxies into one. This is what exists inside Andromeda. Not just a faint smudge, but a vast empire containing 1,000,000,000,000 suns, spiral arms where new stars are born, a central monster sleeping at the core, companions being slowly devoured, streams marking past victims, and an enormous invisible halo containing most of the galaxy's mass. all of it approaching us, falling toward the Milky Way with unstoppable momentum, destined to collide in a future so distant that everything you know will be ancient history. And among all those stars, orbiting all those suns, scattered throughout a galaxy larger than our own, there might be worlds where life exists. Beings who look up at their night sky and see our Milky Way as a faint blur of light, wondering if anyone else is out there, asking the same questions we ask, feeling the same curiosity and loneliness that drives us to search the sky for signs of other minds. If they exist, we'll never meet them. The distance is too great, the time required too long. Any message we sent would arrive in the distant future, and any reply would take just as long to return. By the time we heard back, everyone who sent the original message would be long dead, their civilization possibly extinct, Earth itself possibly uninhabitable. Communication across intergalactic distances isn't just difficult. It's effectively impossible. The delay is so long that meaningful exchange becomes absurd. So if there are beings in Andromeda looking at our galaxy right now, wondering if we exist, they'll likely die without ever knowing the answer. And we'll die without ever knowing if they existed. We'll spend our brief lives separated by a gulf that light itself takes ages to cross. Two civilizations existing simultaneously in the same universe, but unable to bridge the distance between us, forever isolated by the vast emptiness of intergalactic space. This is the loneliness of the cosmos. Not just physical isolation, but temporal. The delays so long that even at light speed, even using the fastest method physics allows, communication becomes meaningless. We can see Andromeda. We can study it, map it, understand its structure. But we cannot touch it, cannot reach it, cannot know what exists on planets orbiting its trillion suns. It remains forever beyond our grasp, beautiful and mysterious and completely isolated from us by distance and time. Yet despite this isolation, despite knowing we'll never reach Andromeda or communicate with anyone who might live there, there's something profound about understanding what it is. That faint blur visible from Earth isn't just an astronomical object. It's a place, a vast structure containing multitudes, shaped by billions of years of history, bearing scars from past violence, surrounded by the slowly dissolving remnants of galaxies it has consumed, all embedded in an invisible halo of mysterious dark matter. And this entire system, this empire of a trillion suns, this cannibal galaxy that has already devoured its neighbors and is currently tearing apart its remaining satellites, is approaching us. The collision is guaranteed. The physics is clear. The trajectory is set. And when Andromeda and the Milky Way finally meet, when they begin the slow process of merger that will take millions of years to complete, everything we can see will be transformed into something new. You are already inside Andromeda, not the visible part. The galaxy you see in the night sky, that faint smudge of light, is still impossibly distant. The stars that create that glow are separated from us by a void so vast that their light has been traveling since before your species existed. But Andromeda is more than just the stars you can see. Like all galaxies, it's surrounded by something invisible, something that extends far beyond the visible disk, reaching out into the darkness with ghostly fingers you cannot perceive, dark matter. A halo of mass that doesn't emit light, doesn't absorb it, doesn't interact with anything except through gravity. And that halo is enormous, extending outward from Andromeda's center across distances that dwarf the visible galaxy itself. While Andromeda's bright disk spans perhaps 200,000 light years, the dark matter halo reaches 10 times farther, creating a vast invisible structure that contains most of the galaxy's mass. And the outer edges of that halo, the furthest reaches of Andromeda's gravitational influence, are already touching the Milky Way's own dark matter halo. The two galaxies, though their visible parts remain separated by the void, are already in contact, already connected, already influencing each other through gravity that reaches across the emptiness. This isn't speculation. Astronomers have measured it, mapped the extent of Andromeda's halo, traced its reach across space. Right now, at this moment, particles from Andromeda's dark matter halo are passing through the space where you sit. They're all around you, invisible, undetectable by any sense you possess, but real. You exist within the outer boundaries of Andromeda's influence. The collision hasn't just begun in some abstract future sense. It's happening now. It's been happening. We're already living through the earliest stages. The visible collision, the spectacular display when stars from both galaxies fill the sky together, when spiral arms interpenetrate and gas clouds ignite into vast waves of star formation. That's still ages away, but the gravitational dance has already started. Andromeda's mass and the Milky Way's mass are already pulling on each other, already influencing each other's motion through space. The approach is underway. The merger is in progress. We just can't see it yet with our eyes, but you can see evidence of the approach in other ways. Every second, the gap between the galaxies shrinks. While you've been reading this, while you've been breathing and existing and going about your life completely unaware, Andromeda has moved measurably closer. The distance that separates our galaxy from theirs is slightly smaller than it was when you started reading, and it will be smaller still when you finish. The approach is constant, relentless, unstoppable. This movement violates the fundamental pattern of cosmic expansion. Point a telescope at any distant galaxy and measure its light, and you'll see wavelengths shifted toward red, stretched by the galaxy's recession as space itself expands. Everything in the observable universe is moving away from everything else, carried apart by the expansion of space, except Andromeda. Andromeda's light is shifted toward blue, compressed rather than stretched, revealing that the source is approaching rather than receding. The approach speed is immense by human standards, but glacial on cosmic scales. Andromeda is closing the distance faster than any spacecraft we've built, faster than we've ever traveled, racing toward us with unstoppable momentum. But the remaining gap is so vast that even at this tremendous speed, the final collision won't occur for billions of years. The merger unfolds over timescales that make human history seem instantaneous, an eye blink, a moment too brief to measure. Yet the approach is inevitable. Nothing can stop it. No force exists that could alter these trajectories, no intervention that could prevent what's coming. The galaxies are falling toward each other under mutual gravitational attraction, following paths set billions of years ago when they first formed from collapsing clouds of dark matter and gas. The collision has been scheduled since the beginning, written into the initial conditions of the local group, guaranteed by physics that doesn't care about human concerns or timescales. This creates an eerie feeling when you truly comprehend it. Something vast beyond imagination is approaching, something containing more mass than you can calculate, following a trajectory that will eventually intersect with our entire galaxy, and there's nothing anyone can do about it. No technology we could develop, no intervention we could make would be sufficient to alter the course of galaxies. We're watching a collision unfold in ultra-slow motion. Passengers on one of the objects involved, completely unable to affect the outcome. But understanding the collision requires shifting your perspective on time. Human lifetimes are brief, barely long enough to notice the seasons changing, the years passing, the gradual aging of familiar things. Civilizations rise and fall over centuries or millennia, and even that seems like a long time from a human perspective. But the collision between Andromeda and the Milky Way will unfold over timescales that dwarf anything in human experience. The galaxies won't crash together in a moment of violent impact. They'll interpenetrate slowly, taking millions of years to complete the first passage through each other, then millions more to fall back together, then millions more for subsequent encounters, until finally the merger is complete and both galaxies have lost their separate identities. The entire process, from first contact to final equilibrium, will span timescales comparable to how long complex life has existed on Earth. From a human perspective, the collision is so far in the future that it might as well be never. By the time the merger begins in earnest, the Sun will have evolved into something very different from what it is today. Earth will have been transformed by solar evolution, by continental drift, by whatever happens to life on its surface over billions of years. The continents will be in different positions. The climate will be unrecognizable. The atmosphere might be different. Whatever exists on Earth when the collision begins, if anything does, won't resemble the world we know. And humanity? Our species almost certainly won't survive unchanged for that long. Species don't persist for billions of years. They evolve, they change, they split into new forms, or they go extinct. By the time Andromeda and the Milky Way collide, our descendants, if any exist, will be so different from current humans that we wouldn't recognize them. They might be biological, evolved into new forms. They might be technological, having transcended biology in ways we can't imagine. They might have spread to other stars, other galaxies. Or they might be gone entirely, extinct, replaced by other forms of life, or leaving behind a barren Earth orbiting an aging sun. Yet despite this vast temporal separation, despite the certainty that no current human will witness the collision, there's value in trying to imagine what it would be like. What would someone experience if they could somehow exist during the merger? What would the sky look like? What would happen to stars and planets and any life that might persist? Even if the answers are purely imaginative, even if no human will ever actually see these events, thinking about them reveals something about the universe's nature and our place within it. The approach has a timeline, stages that will unfold in sequence as the galaxies draw nearer. Right now, tonight, the galaxies are separated by visible matter. You look up and see Andromeda as a distant blur. Someone in Andromeda looking back would see the Milky Way the same way, a faint smudge, separate and distant. But the dark matter halos are already touching, already interacting, the invisible components of both galaxies beginning to merge even while the visible parts remain apart. Over the next billion years, the approach will continue. Andromeda will grow brighter in Earth's sky, assuming Earth still exists and has observers looking up. What is currently a faint smudge visible only under dark skies will become obvious, unmistakable, a spiral structure showing detail, even to unaided eyes. The spiral arms will become visible, individual bright stars will resolve. The companion galaxies orbiting Andromeda will appear as separate patches of light. The night sky will change, slowly but measurably, Andromeda growing larger with each passing million years. And then, in the distant future, the visible collision will begin. Not with a crash or explosion, but with gradual interpenetration, the outlying regions of both galaxies beginning to intermingle, stars from each system sharing space, gravitational influences that were once negligible becoming significant. This is when the transformation becomes undeniable, when anyone looking up would know that something unprecedented is happening, that the sky itself is being reorganized by forces beyond comprehension. For millions of years before the visible collision begins, the sky will be changing, slowly, imperceptibly over human lifetimes, but changing nonetheless. Andromeda has been growing brighter and larger in Earth's sky since it first became visible, and it will continue growing, the distant blur transforming into something more substantial, more present, more impossible to ignore. Imagine standing on Earth, or what remains of it, billions of years from now. The planet might still exist, though transformed by time beyond recognition. The continents have drifted to new configurations. The oceans might be gone, boiled away by a sun grown hotter with age. The atmosphere might be different, altered by billions of years of geological and biological processes. But if you could stand there and look up, you would see a night sky profoundly different from the one we know. Andromeda dominates. What was once a faint smudge now spreads across a significant portion of the sky, a great spiral of light showing structure visible to the naked eye. You can see the spiral arms, bright lanes winding through the galaxy, regions where young stars blaze with fierce light. You can see the central bulge, a concentrated glow marking the dense stellar core. You can see the two companion galaxies orbiting around Andromeda like smaller attendants, each one a patch of light distinct from the main system. But Andromeda isn't alone anymore. The Milky Way's disk, which ancient humans could only see as a band of light crossing their sky, is now visible from an external perspective as the galaxy's positions have shifted relative to each other. What was overhead is now offset, tilted, showing its full structure. Two spiral galaxies occupy the sky together, each one vast, each one beautiful, separated by a gap that's still immense, but no longer seems infinite. The sky is brighter than it has been in billions of years. The combined light of both galaxies illuminates the night. There are so many stars visible, so many points of light scattered across the darkness, that the constellations ancient humans knew are lost, buried in the crowd. New patterns might be traced if anyone bothered, new arrangements of bright stars forming shapes that have no names, no myths, no meaning, except as markers in a transformed sky. And the sky continues changing, not over millions of years anymore. The transformation is accelerating, becoming faster, measurable over shorter periods. Andromeda is still approaching. The gap continues closing. And soon, very soon on cosmic timescales, something new will begin. The outer regions of both galaxies, the sparse halos where stars are scattered widely, will start to overlap. The first stars to intermingle will be the outlying ones, members of each galaxy's halo orbiting far from the dense central regions. These are old stars mostly, red giants and white dwarfs, and ancient suns that formed early in their parent galaxies' histories. As the galaxies approach, these halo stars begin passing through each other's territories, their paths bringing them into regions that now contain stars from both systems. But the stars don't collide. This is important to understand. Space is so vast, the distances between individual stars so enormous that even when galaxies merge, stellar collisions are extraordinarily rare. Stars are like grains of sand scattered across a continent. You could bring two continents together, overlap them completely, and the individual grains would almost never touch. They'd pass through the spaces between each other, their positions shifted by the continent's movement, but the grains themselves remaining intact. The same applies to stars during galaxy mergers. They'd pass like ghosts through each other's formations, their paths altered by the collective gravitational field of both galaxies, but the stars themselves remaining untouched. A star from Andromeda might pass within light years of a Milky Way star, close by cosmic standards, but still vastly too far for any direct interaction. The stellar populations interpenetrate, mixing together, but individual stars continue orbiting, continue burning, continue existing as they did before the merger began. The gas is different. While stars pass through each other without colliding, the diffuse clouds of gas that fill the space between stars do collide. When gas clouds from both galaxies meet, they compress each other, they heat up, they create shock waves that propagate through the material. And in those compressions, in those violent encounters between clouds that were previously separate, something extraordinary happens. Stars begin to form, thousands of them, millions. The collision triggers the greatest episode of star formation either galaxy has experienced in billions of years. Gas clouds compressed by the encounter collapse under their own gravity, fragmenting into clumps that ignite fusion, creating new suns throughout both galaxies. These stellar nurseries blaze with the light of young, hot stars, blue-white giants that pour ultraviolet radiation into their surroundings, illuminating the clouds they formed from. From the ground, if you could witness this from a planet that survives the chaos, the sky would be transforming in ways beyond description. New bright stars would appear, regions that were dark suddenly glowing with the light of stellar birth. The rate of supernova explosions would increase as massive young stars burn through their fuel quickly and die catastrophically, their detonations briefly outshining entire regions of both galaxies. The night sky would never be stable. Each year, each century, each millennium would bring changes. Stars would appear in new positions as orbital paths are disrupted by gravitational chaos. Bright new suns would blaze into existence in star-forming regions. Supernova would flare and fade, their expanding remnants creating shells of glowing gas visible for thousands of years. The familiar patterns, any constellations that might have been traced, would dissolve and reform, the sky becoming something fluid and dynamic rather than fixed. And through all of this, the galaxies continue their dance. They don't simply pass through each other once and separate. Gravity ensures they'll interact repeatedly. After the first passage, after interpenetrating and emerging on opposite sides, both galaxies slow their separation, stop, reverse course. They fall back together. They collide again, passing through each other a second time, each encounter rearranging the stellar populations further, triggering new waves of star formation where gas clouds collide again. This process repeats. The galaxies merge and separate, each passage bringing them closer together, each encounter mixing their stars more thoroughly. With each collision, the orbital energy is dissipated through gravitational interactions, the galaxies losing momentum, their paths bringing them together more tightly. The time between successive passages decreases. What was millions of years becomes hundreds of thousands, then less, the encounters becoming more frequent as the merger progresses. During these repeated collisions, the spiral structures begin to dissolve. The beautiful arms that characterized both galaxies, the elegant patterns traced by young stars and glowing gas, are disrupted by gravitational chaos. Stars that once followed orderly circular orbits in the galactic disk are flung into new trajectories, some diving toward the center, others ejected toward the outer regions. The organized rotation that maintained the spiral pattern is destroyed, converted into random motion, the disks puffing up and losing their flat structure. And at the very centers of both galaxies, something momentous is occurring. Each galaxy harbors a supermassive black hole at its core, a gravitational monster containing millions of times the Sun's mass. As the galaxies merge, these black holes are being drawn together, each one sinking toward the center of the combined system through a process driven by stellar interactions and gravitational forces. The black holes orbit each other, initially at large distances, but gradually spiraling inward as they lose energy. Stars venture too close and are flung outward at tremendous speeds, their gravitational encounters with the black holes robbing orbital energy and causing the black holes to fall closer together. This process takes time, millions of years, but it's inexorable. The black holes spiral inward, their orbital period decreasing, their velocities increasing as they approach. Eventually, they merge. Two supermassive black holes, each containing the mass of many millions of suns, combine into one. The merger releases energy in gravitational waves, ripples in space-time itself that propagate outward at light speed. Any detectors existing billions of years in the future, if any civilization is still building such instruments, would record the signal. A chirp in their data frequency increasing as the black holes spiral together, then cutting off abruptly when merger completes. The combined black hole settles into its new equilibrium, more massive than either parent, surrounded by a dense stellar core built from stars of both galaxies mixed together. This merged core is hotter and denser than the cores of either parent galaxy were before collision. Stars orbit faster here, pass closer to each other, exist in an environment transformed by the violence of merger. But the merger doesn't just affect the central regions. Throughout both galaxies, throughout all the volume that the stellar populations occupy, the collision is reorganizing everything. Our sun, if it still exists at this point, which is questionable given solar evolution, will have been pulled into a new orbit around the merged galactic center. It might be drawn inward, falling toward the dense core regions where stellar encounters are more frequent and the sky is brighter. Or it might be flung outward, ejected toward the outer reaches of the merged system, or even beyond, becoming a rogue star, drifting through intergalactic space with whatever planets remain in orbit. The sun's fate depends on countless factors impossible to predict. Where exactly it was when the galaxies first collided, how close it passed to massive structures during the encounters, random gravitational interactions with other stars or with dense clumps of matter. The outcome is determined by chaos, by the accumulation of countless small influences that amplify over time into large changes. Our solar system could end up almost anywhere in the merged galaxy or outside it entirely, with no way to predict which outcome will actually occur. And Earth, if it still orbits the Sun, will experience this relocation as a change in its night sky. The stellar neighbors visible from Earth will be different. A mix of Milky Way natives and Andromeda immigrants, stars from both galaxies now sharing the same space. The galactic center will be in a different direction than it was before the merger. Possibly closer and brighter, possibly farther and dimmer. The sky will be reorganized completely. Every familiar pattern erased, replaced by arrangements that would be unrecognizable to anyone who saw Earth's sky before the collision. But there's another factor affecting Earth's fate that has nothing to do with the galaxy collision. By the time the merger occurs, the Sun will have evolved significantly from its current state. It's been burning hydrogen in its core for billions of years, and that fuel won't last forever. The Sun is gradually getting hotter, slowly brightening as nuclear fusion becomes more efficient in its aging core. This brightening has consequences for Earth. Over the next billion years or so, the increasing solar radiation will begin to affect Earth's climate profoundly. The oceans will start to evaporate, water vapor filling the atmosphere. Because water vapor is a greenhouse gas, this will trap more heat, accelerating the warming and a runaway feedback. Eventually, the oceans will boil away entirely. Earth will become a Venus-like world, hot and dry, with a thick atmosphere but no liquid water, no conditions suitable for life as we know it. By the time the galaxy collision is well underway, Earth will almost certainly be lifeless. The oceans will be long gone. The atmosphere might be stripped away by solar wind as the Sun evolves. The surface might be hot enough to glow, and eventually the Sun will swell into a red giant, expanding to perhaps encompass Earth's orbit entirely. The home of humanity will be destroyed not by the galactic collision, but by the natural evolution of its own star. This is the tragedy underlying the collision. All the spectacular cosmic violence, all the star formation and black hole mergers and gravitational chaos occurs too late to matter for humanity's birthplace. Earth won't survive to see the merger's completion. The Sun won't live long enough in its current form to orbit in the final merged galaxy. Everything that happened on Earth, every form of life that evolved here, every human who lived and died, all of it will be ancient history long before Andromeda and the Milky Way finish merging. Yet the collision will be witnessed if life and intelligence persist in some form. Our descendants, if they exist, will have left Earth long before it became uninhabitable. They might have spread to other stars in the Milky Way, building civilizations on worlds orbiting younger suns that will still burn when the merger occurs. They might exist in forms we can't imagine, having transcended biology or changed so profoundly that we wouldn't recognize them as descendants of humanity. But they might be there, somewhere in the merging galaxies, watching the transformation unfold. And what they would witness is the birth of something new. Not just the death of two galaxies, but the creation of a single larger structure, a merged system containing everything both parents possessed, transformed by collision into a configuration neither was before. The merger is destructive, yes. It tears apart the ordered structures both galaxies spent billions of years building. But it's also creative. The star formation, triggered by gas-cloud collisions, creates millions of new suns that wouldn't have existed without the merger. The combined mass creates a galaxy more substantial than either parent. Something new is being born from the collision of two old systems. The peak of the collision, the phase when the merger's effects are most visible and dramatic, unfolds over millions of years but would appear almost static from a human perspective. If you could somehow witness a single moment during this peak, frozen in time, what you would see is two galaxies occupying the same space, their stars thoroughly mixed, their structures completely interpenetrated. Look up and you see stars everywhere, not arranged in neat spiral patterns anymore, not following the orderly structures that characterized both galaxies before collision. Just stars scattered across the sky in all directions, some bright and close, others dim and distant, filling the darkness with points of light that have no pattern, no organization, no relationship to the constellations that ancient peoples might have traced. Many of these stars are new, born during the collision from gas clouds compressed by the encounter. They're young and hot, burning with fierce blue-white light that will last only a brief time in cosmic terms before they exhaust their fuel and die. These stellar infants are scattered throughout both galaxies, marking regions where gas clouds from the Milky Way met gas clouds from Andromeda, and the collision triggered collapse and ignition. The star formation happens in waves, surges of stellar birth, corresponding to each passage of the galaxies through each other. When the systems first collided, when their gas clouds first encountered each other, that initial compression created the first wave of new stars. Then the galaxies separated, the gas clouds moving apart, and star formation subsided. But when the galaxies fell back together for their second collision, the gas clouds met again, compressed again, triggering another wave of stellar birth. Each wave is different. The first collision compressed relatively fresh gas, material that hadn't been significantly disturbed since the galaxies formed. This gas was rich in hydrogen and helium, the raw materials for star formation, and it collapsed readily when compressed. The resulting stars were predominantly massive, blue giants that formed quickly from the densest clumps and began pouring radiation into their surroundings almost immediately. But subsequent collisions worked with gas that had already been disturbed, heated, partially ionized by radiation from stars formed during earlier waves. This gas was more difficult to compress, requiring stronger shocks to overcome the pressure support from its higher temperature. The stars that formed during later collisions tended to be smaller on average, taking longer to accumulate enough mass to ignite fusion, burning more steadily once they did. Throughout all these waves of star formation, the rate at which new stars appear fluctuates wildly. During the collision peaks, when gas clouds are being compressed most violently, stars form at rates hundreds or thousands of times faster than the steady background rate either galaxy maintained before merger. Between collisions, when the galaxies are separating and gas has time to settle, star formation drops back to normal or even below normal levels as the available gas is temporarily exhausted. This creates a characteristic signature visible in the merged system's stellar population. If you could somehow measure the ages of all the stars, you would see distinct generations corresponding to each collision, separated by gaps representing the periods between encounters. The youngest generation would be forming now during the current collision. Slightly older stars would date from the previous encounter. Even older stars would mark earlier collisions, each wave leaving its imprint in the form of stars whose ages cluster around specific values. And between all these collision-formed stars, the older stellar populations from both parent galaxies continue existing. Ancient red giants that formed billions of years ago, before either galaxy began approaching the other. Yellow suns, like our sun was, stable and steady, formed in earlier eras of normal star formation. Cool red dwarfs that will burn for trillions of years, outlasting everything else, formed early in both galaxies' histories and still orbiting, still shining, still converting hydrogen to helium in their cores, despite all the chaos occurring around them. The mixing of these populations creates strange juxtapositions. A star that formed in Andromeda 10 billion years ago might now orbit next to a Milky Way star of similar age. The two suns sharing space despite having originated in different galaxies, having spent most of their lives separated by a void neither could cross. They pass each other without interaction, without collision, their paths bringing them close by cosmic standards, but still vastly too distant for any direct influence. And scattered among all these stars, the old and the new, the native and the foreign, are the debris of stellar death, supernova remnants, expanding shells of hot gas created when massive stars exploded. Planetary nebulae, beautiful structures formed by dying stars shedding their outer layers, white dwarfs, Earth-sized remnants cooling slowly in the darkness, neutron stars, incredibly dense corpses spinning rapidly and beaming radiation into space, black holes, stellar mass monsters lurking invisibly, revealed only when they pull material from companion stars and heat it to X-ray temperatures. The rate of supernova during the merger is elevated significantly above normal. All those young, massive stars born during collision waves live fast and die young, burning through their nuclear fuel in just millions of years before collapsing and rebounding in catastrophic explosions. Each supernova briefly outshines billions of normal stars, creating a brilliant point of light visible across the entire merged system, flooding its surroundings with radiation and heavy elements forged in the explosion. From a planet somehow surviving this chaos, these supernovae would be spectacular but terrifying. A new star would appear in the sky, growing brighter over days or weeks, eventually becoming so luminous that it casts shadows at night, bright enough to see in daylight. It would remain brilliant for months before slowly fading, leaving behind an expanding remnant that glows for thousands of years as the blast wave heats surrounding gas. If a supernova occurred close enough within a few hundred light years, it could be dangerous. The radiation burst, particularly the gamma rays and X-rays, would arrive at the speed of light, bathing the planet in high-energy radiation capable of damaging the atmosphere, destroying the ozone layer, perhaps even affecting life on the surface. But most supernova would occur at safe distances, spectacular but harmless, distant fireworks illuminating the night sky without threatening the viewers. The gravitational effects during merger are profound and complex. Both galaxies, before collision, had organized rotation. Stars orbited the galactic center in roughly circular paths, all moving in the same direction, creating the flat disk structure characteristic of spirals. But the collision disrupts this organization completely. As the galaxies interpenetrate, stars from each system feel gravitational pull from the other galaxy's mass. A star from the Milky Way passing through Andromeda feels pull from Andromeda's collective mass, in addition to its own galaxy's gravity. This additional force deflects its trajectory, altering its orbit, changing its angular momentum. The star emerges from the collision on a different path than it entered, its neat circular orbit transformed into something more elliptical, more chaotic. Multiply this by billions of stars, each one having its orbit altered in different ways, depending on exactly where it was and what it encountered, and you create complete gravitational chaos. The ordered rotation breaks down. Stars end up on orbits tilted at all angles, some diving through the galactic plane, others looping out to great distances, the flat disk structure dissolving into something more spherical. This transformation from disk to sphere is characteristic of galaxy mergers. When two spirals collide, they usually produce an elliptical galaxy, a roughly spherical distribution of stars with no preferred rotation direction, no organized structure beyond the basic spherical symmetry. The elegant spiral arms, the flat rotating disks, are destroyed by collision and replaced with randomized motion. Some stars are accelerated to tremendous speeds during these gravitational encounters. A star passing near a dense concentration of mass, perhaps near the merging central regions or through a particularly dense stellar cluster, can receive a gravitational kick that boosts its velocity far above normal. These kicked stars become hypervelocity objects, racing through the galaxy faster than escape velocity, destined to eventually leave the merged system entirely and drift through intergalactic space alone. Thousands or millions of stars are ejected this way during the merger. They're flung outward by gravitational encounters with higher probability at the galactic center, where stellar density is highest and encounters are most frequent. These ejected stars carry with them any planets that remain bound, entire solar systems becoming rogue, wandering through the void between galaxies with no parent galaxy to call home. From a planet orbiting one of these ejected stars, the night sky would be strange and lonely. The merged galaxy would be visible as a distant glow, perhaps still showing some structure, but separated by a gulf that's growing as the ejected star races away. In all other directions, darkness. Other galaxies would be visible as faint smudges, but the nearest other structures would be millions of light years distant. The isolation would be total, but most stars aren't ejected. Most remain bound to the merged system, their orbits altered but not so drastically that they escape entirely. These stars become part of the new galaxy's permanent population, their random orbits contributing to the elliptical structure, their ages and compositions creating a mixed stellar population, unlike either parent galaxy possessed. And throughout all of this chaos, the gas continues colliding, continues forming stars, continues driving the transformation. Each collision between gas clouds doesn't just trigger star formation. It also heats the gas, ionizes it, drives it into motion. Some of the gas is compressed enough to collapse and form stars, but much of it is heated to such high temperatures that it can't collapse, instead existing as a hot, diffuse medium filling the space between stars. This hot gas radiates X-rays, energy bleeding away into space as the gas slowly cools. Over millions of years, as the collisions continue and more gas is heated, the merged system develops an extended X-ray halo, a region filled with million-degree gas glowing at wavelengths invisible to human eyes but detectable by X-ray telescopes. Some gas is driven outward entirely, blown away from the merged galaxy by the combined effects of stellar winds, supernova explosions, and radiation pressure from all the young stars formed during collision. This gas escapes into intergalactic space, enriched with heavy elements forged in stars and supernova, carrying the products of stellar nucleosynthesis away from the galaxy that created them. The loss of gas during merger has long-term consequences. Gas is the raw material for future star formation, and losing it means the merged galaxy will form fewer new stars in the future than the parent galaxies would have formed if they'd remained separate. The merger triggers intense star formation in the short term, but it reduces star formation potential in the long term, converting available gas into stars or heating it and expelling it. This is why elliptical galaxies, the products of mergers, are typically dominated by old red stars. They used up most of their gas during the merger that created them, forming many new stars during the collision, but then settling into a quiescent state where new star formation is rare. They age passively, their stellar populations gradually shifting toward older, cooler stars as the young, massive ones die and aren't replaced. But that fate is still in the future. Right now, during the collision's peak, star formation is vigorous. The merged system is alive with stellar birth, with gas clouds collapsing, with new suns igniting across vast regions of both galaxies. It's creative chaos, destruction, and creation occurring simultaneously, the old order being destroyed while something new is being built from the debris. And at the very center, where both galaxies' cores have merged completely, where the supermassive black holes have combined into one, a new galactic nucleus is forming. This dense central region contains stars from both parent galaxies, mixed together and packed into a relatively small volume. The stellar density here is extraordinary, stars passing close enough to each other that they occasionally collide directly, their masses combining to create blue stragglers, stars that appear younger than they should be because collision pumped new fuel into them. The night sky viewed from a planet in this central region would be overwhelming. Thousands of bright stars would be visible, many close enough to show as tiny disks, their combined light creating an environment where true darkness never occurs. The galactic center would glow perpetually, bright enough to cast shadows, bright enough to illuminate landscapes, without any other light source needed. But this central region is also dangerous. The radiation environment is intense, with all those nearby stars pouring out ultraviolet light and X-rays. Any life trying to survive here would face constant bombardment, radiation levels far exceeding what Earth experiences in its relatively quiet galactic suburb. And the gravitational environment is chaotic, with the central black hole and all the nearby stellar mass, creating complex tidal effects that could disturb planetary orbits over time. The merger continues for millions of years, the galaxies passing through each other repeatedly, each encounter mixing their stars more thoroughly, each collision triggering new waves of star formation, each gravitational interaction randomizing orbits further. Slowly, gradually, the separate identities of both galaxies are erased. What were two distinct spirals become one merged system, an elliptical galaxy containing all the mass of both parents, but with structure entirely different from either. The transformation is not instantaneous, and it's not simple, but it's inexorable. The physics guarantees it. And when the process is complete, when the last vestiges of organized rotation have been destroyed and replaced with random motion, when all the gas has been consumed or expelled and star formation has dropped to minimal levels, what emerges is something new. A galaxy that never existed before, born from the collision of two older systems, containing their combined mass, but with characteristics neither possessed individually. This is the peak of the collision, the phase when transformation is most active, when change occurs most rapidly, when the creative destruction of galaxy merger is most visible. It's violent in a slow, cosmic way. It's spectacular beyond anything humans have witnessed. And it's happening, guaranteed to occur, written into the trajectories of galaxies that are already approaching each other with unstoppable momentum. The violence subsides. After millions of years of chaos, after repeated collisions and gravitational upheaval, after waves of star formation and stellar ejections and black hole merger, the system begins to settle. The galaxies have passed through each other for the last time. There will be no more collisions, no more encounters, no more separation and return. The merger is complete. Two have become one. What emerges from this cosmic violence is something different from either parent. Where there were two spiral galaxies, each with elegant arms winding through space, there's now a single elliptical galaxy, roughly spherical in shape, lacking the organized structure that characterized spirals. The flat rotating disks are gone, destroyed by gravitational chaos and replaced with something more random, more three-dimensional. The transformation is total. If you could see this new galaxy from a distance, from another galaxy watching across millions of light years, you would struggle to identify which stars came from which parent. The populations are thoroughly mixed, Andromeda stars and Milky Way stars sharing the same space, orbiting together in the merged system, indistinguishable except through detailed analysis of their ages and chemical compositions. The new galaxy is larger than either parent. It contains all the stars from both the Milky Way and Andromeda, plus millions of new stars born during the collision when gas clouds compressed and ignited. The total stellar population is staggering, approaching or exceeding 1 trillion suns, each one burning hydrogen into helium, each one potentially orbited by worlds, each one a nuclear furnace pouring energy into space. But the galaxy is also more diffuse in some ways than the parent spirals were. The violent encounters ejected many stars to larger orbits, spreading the stellar population across a bigger volume than before. Where the Milky Way and Andromeda each had most of their stars concentrated in relatively compact disks, the merged system has stars distributed more evenly throughout a spherical region, creating a puffier, less concentrated structure. This new galaxy needs a name. Astronomers thinking ahead to this distant future have already coined terms for the merged system. Some call it Milkomeda, a forced combination of both parent names. Others prefer Milkdromeda, slightly more awkward, but perhaps more balanced. The names are utilitarian, lacking poetry, but they serve their purpose. They label the entity that will exist after merger, the galaxy that contains everything the Milky Way and Andromeda were, transformed by collision into something neither was before. At the center sits the merged black hole, a gravitational monster more massive than either of its parents. The two supermassive black holes that once sat at the cores of separate galaxies have combined, their merger creating a single larger object that now anchors the rotation of the entire system. This central black hole is dormant currently, not actively feeding, not blazing with radiation from infalling matter. It has consumed what was available during the merger, and now waits patient and invisible, surrounded by a dense swarm of stars. The stellar core surrounding the central black hole is hot and crowded. This region contains stars from the cores of both parent galaxies, mixed together and compressed by the merger into a volume smaller than either core occupied separately. Stars here orbit rapidly, whipping around the galactic center on tight ellipses, their velocities revealing the tremendous mass concentrated at the center. Occasionally, stars in this dense environment pass close enough to interact. Two stars on intersecting orbits might approach within fractions of a light year, close enough that their gravity affects each other, altering trajectories, potentially even resulting in direct collision if the geometry aligns unfortunately. These stellar collisions are rare but not impossible in such a crowded environment, and they create unusual objects, merged stars with properties different from either parent. Beyond the core, the bulk of the merged galaxy stars orbit in a vast halo, lacking the organized structure the parent disks possessed. There's no preferred rotation direction anymore. Stars orbit on paths tilted at all angles, some diving through the galactic center, others looping out to enormous distances before falling back inward. The motion is chaotic in detail, but balanced overall, the random orientations averaging out to create a stable, long-lived configuration. This randomized motion is what makes the galaxy elliptical rather than spiral. Without organized rotation, without most stars moving in the same direction in a flat disk, you can't maintain spiral structure. The density waves that create and maintain spiral arms require coherent rotation, require stars moving together in coordinated fashion. That coordination is destroyed during merger, and what emerges is a galaxy where stars move independently, their individual orbits bearing no relationship to their neighbors' paths. The galaxy is also redder on average than either parent was. This reddening doesn't happen immediately after merger, but develops over time as the stellar population ages. During the collision, many young blue stars were born, hot, massive suns that burn bright but briefly. But these stellar infants have short lifespans, just millions of years before they exhaust their fuel and explode as supernova. As time passes after merger, as the massive stars die one by one without being replaced, because most of the gas has been consumed or expelled, the galaxy's average color shifts toward red. The cool, long-lived stars remain, while the hot young ones disappear, creating a stellar population dominated by older, redder suns. Eventually, perhaps 1 billion years after merger completes, the galaxy will be recognizably red, a characteristic of elliptical galaxies that have used up their gas and settled into passive aging. But that future state is still distant. Right now, in the era immediately following merger, the galaxy retains some of the gas that survived the collision. Not as much as the parent galaxies possessed before merger. Much of it was consumed during the intense star formation or heated and expelled, but enough remains to allow some continued stellar birth. Pockets of gas collect in certain regions, compress, collapse, form small clusters of new stars. The rate is much lower than during the collision's peak, but it's not zero. Star formation will continue at this low rate for billions of years, gradually exhausting the remaining gas, until finally the last clouds collapse and ignite the last generation of stars. After that, the galaxy will age passively, its stellar population gradually shifting toward older, cooler stars as the remaining young ones die without replacement. The galaxy will slowly redden, dim, cool, entering a long period of quiescence that could last for hundreds of billions of years. But that distant future aging is abstract and difficult to comprehend. What matters in the immediate post-merger era is that something new exists. A galaxy that wasn't there before, built from two older systems containing their combined history and mass. Every star in this merged galaxy has a story. Some formed in the Milky Way billions of years ago, and orbited there for ages before the merger swept them into new trajectories. Others originated in Andromeda, born from different gas clouds, evolving in a different galaxy before collision brought them here. And scattered among these ancient stars are the new ones, the merger generation, born during the collision from gas clouds compressed by violence. These young stars will be the last bright blue giants the galaxy produces in large numbers. After they die, after the remaining gas is exhausted, the galaxy will produce primarily smaller, longer-lived stars from whatever gas remains. The era of massive star formation is ending, replaced by a quieter phase where stellar birth is rare and the galaxy lives primarily on the light of stars already formed. The satellite galaxies that once orbited Andromeda are gone now, absorbed during the merger or shortly afterward. Their stars have been scattered into streams that wrap around the merged galaxy, or they've been completely mixed into the general population, their separate identities erased. What were once distinct galaxies are now just stars orbiting in the merged system, indistinguishable from stars that originated in the parent galaxies except through detailed analysis. But the merger process added structure in other ways. The gravitational violence created shells and streams, coherent features visible in the outer regions where stars following similar orbits create enhanced density. These structures are fossils of the merger, markers showing where particular groups of stars were flung during specific encounters. They'll remain visible for billions of years, slowly dispersing as the orbits drift apart, eventually mixing into the background, but persisting long enough to serve as evidence of the galaxy's violent formation. The dark matter halo has also merged completely. The two separate halos that once surrounded the Milky Way and Andromeda are now one, a single vast structure containing the merged galaxy's visible components. This dark matter provides the gravitational potential well that holds everything together. The mass that keeps stars in their orbits prevents the galaxy from flying apart. And this merged dark matter halo is enormous, extending far beyond the visible galaxy's boundaries, reaching out perhaps 1,000,000 light-years from the center. Most of the merged galaxy in terms of spatial extent and mass is this invisible halo. The visible stars and gas, spectacular as they are, represent only a small fraction of what exists here. The merged galaxy exists within a larger context. It's part of what was once a local group, a small cluster of galaxies bound together by mutual gravity. But the merger has reorganized the local group's structure. The two largest members, the Milky Way and Andromeda, are now one. The smaller galaxies that once orbited them separately now orbit the merged system, their populations diminished by tidal stripping, their futures uncertain. Some of these smaller systems will be absorbed eventually, pulled into the merged galaxy and torn apart by tidal forces, their stars added to the general population. Others might survive at safe distances, maintaining their separate identities, continuing to orbit as satellites. The outcome depends on their current positions and velocities, factors determined by the chaos of the merger and difficult to predict. But whether they survive or are absorbed, these smaller galaxies are now part of a system dominated by the merged giant. The gravitational landscape has been completely reorganized. What was once a local group with two large galaxies and many small ones is now a system, with one dominant galaxy and diminishing satellites, the structure simplified by merger, the mass concentrated, and this merged system continues its motion through space. The collision between the Milky Way and Andromeda didn't occur in isolation. Both galaxies were already falling toward the Virgo cluster, a much larger collection of galaxies located millions of light years away. That motion continues after merger. The merged galaxy, now more massive than either parent, continues falling toward Virgo, drawn by the combined gravity of thousands of galaxies. Eventually, billions of years from now, the merged galaxy might join the Virgo system, might itself merge with other large galaxies there, becoming part of an even larger structure. This is the hierarchy of cosmic structure formation playing out over incomprehensible timescales. Small galaxies merge to form larger ones. Large galaxies merge to form ellipticals. Ellipticals merge to form even larger ellipticals. The process continues, building larger and larger structures until eventually all the galaxies in a cluster might merge into a single supergalaxy containing the combined mass of thousands of original systems. But that fate is so far in the future, requires so many additional mergers, involves such vast timescales, that it's almost abstract. What matters now, in this era following the Andromeda Milky Way merger, is that something new exists. A galaxy born from collision, containing the legacy of two parent spirals, shaped by violence into something different from either. This is the galaxy that rises from merger, not a continuation of the Milky Way or Andromeda, but something genuinely new, containing elements of both but with characteristics neither possessed individually. It's larger, more massive, more evolved. It's used up much of its gas and will age faster than the parent galaxies would have aged separately. It's structurally different, elliptical rather than spiral, random motion rather than organized rotation. And it exists in a transformed local group, dominating a region that once contained two large spirals as rough equals. The balance has shifted, the merger has simplified, and what was once a dynamic system with multiple large members is now dominated by a single merged giant, the product of billions of years of gravitational evolution, culminating in the collision we've been describing. This is what rises from the chaos. This is what the collision creates. Not just destruction, but transformation, two old things dying, and one new thing being born from their combined remnants. The merger is an ending and a beginning simultaneously, the death of two galaxies and the birth of one, creative destruction on the largest scales the universe allows. So the galaxies will collide. Billions of years from now, Andromeda and the Milky Way will merge, creating something new from the union of two old systems. The process will be spectacular, transformative, creative, and destructive simultaneously. And then it will be over, the merger complete, the new galaxy settling into its equilibrium state. But here's the question that demands an answer. Why should you care? The collision is unimaginably distant. You will be dead. Everyone you know will be dead. Human civilization, if it still exists, will be transformed beyond recognition. Earth itself will likely be uninhabitable or destroyed by solar evolution long before the merger completes. Nothing that happens during the collision will affect you or your descendants for thousands of generations. From a purely practical perspective, the merger is irrelevant to human concerns. We have immediate challenges that matter far more to actual lives being lived right now. The galaxy collision won't help solve any current problems, won't improve anyone's life, won't change anything about the world we actually inhabit. Yet there's value in understanding it anyway. Not practical value, but something deeper, something that has to do with perspective and meaning and our place in the cosmos. Understanding the collision forces you to confront scale. The timescales involved dwarf anything in human experience. Billions of years is not a duration you can truly comprehend. It's vastly longer than human civilization has existed, longer than our species has existed, longer than complex life has existed on Earth. The merger will unfold over timescales that make the entirety of human history seem like an eye blink, a moment too brief to measure, and the spatial scales are equally incomprehensible. The distance between galaxies, the sizes of the structures involved, the number of stars affected, these are quantities beyond human capacity to truly grasp. We can state the numbers, but we can't really feel their magnitude. 1 trillion stars is not something you can hold in your mind. It's too large, too abstract, too far beyond everyday experience. Confronting these scales reveals something important. You are unimaginably small, not just physically, though that's true, but temporally and spatially, you're insignificant. A human lifetime is cosmically brief. Earth is a speck. Our entire galaxy is just one of billions. And even our galaxy is temporary, something that will merge and transform and eventually dissipate over timescales beyond comprehension. This could be depressing. It could make everything seem meaningless. If we're so small and so brief, if nothing we do will matter billions of years from now when the galaxies collide, then what's the point of anything? But there's another way to see it. Yes, we're small. Yes, we're brief. Yes, we're cosmically insignificant in terms of mass and duration and spatial extent. But we're also the only thing we know of that can understand any of this. Stars don't know they're temporary. Galaxies don't contemplate their own mergers. The universe unfolds automatically, mindlessly, just matter and energy following physical laws without awareness, but you're different. You're matter that became aware of itself. You're the universe looking at itself and comprehending what it sees. And that makes you significant in a way that has nothing to do with size or duration. A single human mind contains more complexity and meaning than 1 billion lifeless stars. The collision matters because you can understand it. You can look at Andromeda and know what you're seeing. Not just light, but a galaxy approaching us, destined to merge with ours. You can trace the trajectory forward billions of years and predict the outcome. You can imagine what the collision will be like even though you'll never witness it. That capacity to know, to comprehend, to understand is extraordinary. It's what makes us matter despite our insignificance. And thinking about the collision provides perspective. Your problems, whatever they are, exist in a brief moment of cosmic time. They're real and important to you, but they're also temporary, invisible on the scales we're discussing. Recognizing that doesn't solve your problems, but it does provide context. There are larger patterns, longer time scales, bigger pictures. The collision also reveals something about the nature of existence. Everything is temporary. Everything changes. Everything transforms into something else. Galaxies collide and merge. Stars form and die. Even the structures that seem most permanent are just temporary configurations of matter and energy that will eventually reorganize into new forms. This impermanence could be frightening, but it can also be liberating. Yes, you're temporary. Yes, everything you build will eventually crumble, but that's normal. That's how the universe works. Accepting impermanence, really accepting it, frees you from the fear of change and loss. And there's something else worth considering. While we won't witness the collision, our actions now might influence who or what does witness it. If humanity survives, if we spread beyond Earth, if we persist through the billions of years between now and merger, our distant descendants might be there to see it. They might study the collision, record it, try to understand it, and they'll be able to do that because we now built the foundation. We developed the science, the technology, the understanding that makes space exploration possible. So thinking about the collision isn't just abstract philosophy. It's part of becoming a species that might persist long enough to witness cosmic events on these timescales. Every advance in understanding, every mission to space, every effort to ensure humanity's long-term survival contributes to a future where our descendants might experience things we can only imagine. The collision reveals what we are, small but aware, brief but capable of understanding, insignificant by cosmic measures, but extraordinary in our consciousness. We're the universe knowing itself. Brief as we are, temporary as everything is, we exist in this moment with the capacity to comprehend scales and timescales that dwarf us. And that's remarkable. Look up tonight. Find that faint smudge of light above Andromeda's outstretched arm. That pale blur is a galaxy, a trillion suns burning across a void so vast that their light has been traveling toward you since before your species learned to speak. And it's approaching, getting closer, falling toward us with unstoppable momentum. You cannot stop it. You cannot change its trajectory. You cannot prevent what's coming. The collision is guaranteed, written into the physics of the universe, scheduled billions of years ago when these galaxies first formed. All you can do is watch, understand, appreciate the scale and inevitability of what you're witnessing. This is what Andromeda teaches. Distance. There are places in the universe you cannot reach, destinations forever beyond your grasp, no matter how desperately you might want to go there. Some horizons cannot be crossed. Some mysteries cannot be solved, and that's okay. Not everything needs to be accessible. Some things can remain distant, beautiful precisely because you cannot touch them. Time. The collision will happen in a future so remote that it might as well be never. Billions of years separate you from that event. Timescales so vast that human civilization will likely be extinct or evolved beyond recognition long before the galaxies meet. Everything you know will be ancient history. Everything familiar will be gone. The universe continues far longer than you do, and accepting that reveals your place in the cosmic timeline. Change. Nothing is permanent. Galaxies collide and merge. Stars form and die. Even the most stable structures are temporary on cosmic scales. Everything transforms into something else eventually. Accepting this impermanence, really feeling it, changes how you see existence. Your brief moment matters not despite being temporary, but because it's temporary, precious because it's finite. Perspective. You are small, cosmically insignificant. Brief beyond measure in a universe billions of years old. But you're also extraordinary because you're aware. Because you can look at Andromeda and comprehend what you're seeing, because your consciousness embedded in the cosmos, matter knowing itself. The galaxies will collide whether you understand it or not. The merger will proceed according to physics that don't care about human concerns. But understanding it, truly comprehending what's happening and what will happen, transforms you from passive observer to conscious witness. You're not just watching the universe unfold. You're part of it, aware of it, capable of appreciating the vast processes that shaped everything, including you. So look up tonight. See that distant light. Know that it's a galaxy approaching ours, that billions of years from now they will collide and merge and transform into something new. Know that you're witnessing something guaranteed to happen, inevitable, already in progress through dark matter halos, already touching. And know that in simply being aware of this and understanding what you're seeing, you're participating in something extraordinary. You're the universe knowing itself. Brief as you are, small as you are, your consciousness arising from matter, awareness emerging from unconscious processes, meaning existing in a cosmos that's mostly meaningless. The galaxies will collide. Stars will form and die. Black holes will merge. And through it all, for this brief moment, you're here to witness it, to understand it, to be aware. That's the vision Andromeda offers. Not escape from limitations, but acceptance of them. Not promises of reaching impossible destinations, but appreciation of beauty from afar. Not permanence, but meaning in the temporary. Not answers, but questions worth asking. You're small, brief, limited, finite. And you're also aware, conscious, capable of comprehending vastness beyond yourself. The light from Andromeda will continue reaching Earth long after you're gone. And billions of years from now, when the collision finally occurs, whatever witnesses it won't be human, as we understand the term. But they might be our descendants, carrying forward the legacy of consciousness that began on a small planet orbiting an unremarkable star. Or perhaps there will be no witnesses. Perhaps consciousness is rare and brief, arising and fading, leaving the universe to continue unwatched. We can't know. But right now, in this moment, you know, you understand. You're aware of Andromeda approaching, of the collision to come, of your place in the cosmic story. And that awareness is the most extraordinary thing in the universe. The Cannibal Galaxy approaches, and you're here to watch it happen.